Hello everyone and welcome to this lecture. Up to the lectures we have seen so far and have done so far, we have only considered homogeneous second order differential equations with constant coefficients. But today we are going to start our discussion on non-homogeneous ordinary differential equation. That is, instead of having a zero on the right hand side of the differential equation, we are going to have some function that is denoted by this f over here. And this kind of equations are called non-homogeneous ordinary differential equations, and these ABCs, as usual, the constant coefficients. So solving this kind of equations are pretty hard in general. Sometimes even it may not be solvable, but we will try to see two methods. One of them will be discussed in this video and the other will be in the next video. So let me just write down today's method that we are going to use, and this is called the method of undetermined coefficient. So let me call this technique 1. And we are calling it method of undetermined coefficient. And we would like to show you how we can use this method to solve this equation. Let's call this the equation number 1. So before we dive into the examples, we need to notice something first. Our f of t can have a general form as following. So general form of f of t, and that will be f of t can be written as e to the power lambda t. There will be some pn. I will explain what these terms are in a few seconds. Then you will have a cosine mu t plus qn, which is also a function of this independent variable t, times a sine mu t. Now you might have a lot of questions. What are this lambda, pn, mu, and all these stuffs are, and where are these stuffs coming from? So this kind of the motivation to write this kind of function is coming from solving the homogeneous part of this equation 1. That is where f of t is equals to 0. So let me just write down what are these parameters are. So this pn and qn are n degree polynomials. So your function f of t can be a polynomial function, and it might have some sinusoidal parts, and also at the same time it might have some exponential parts. So that's why these things are written like this over here. Okay, and so let me just write it down. P and t, q and t, these are n degree polynomials, and this lambda and mu, they are actually coming from solving the homogeneous equation. Lambda and mu comes from solving the auxiliary equation that you saw in the earlier lectures. So it is coming from solving the auxiliary equations for the homogeneous part. And since we have cleared what are these parameters, now what we want to do is that we want to see the solutions of equation 1. So solution of equation 1. So the solution can be written as, this is the full solution, can be written in the following way. If where you have a complementary solution and a particular solution. So the complementary solution is denoted by yc, and this particular solution is actually coming from the non-homogeneous part. And this is called the particular solution. And if you recall that if you had a equation like this, where on the right hand side there will just be 0, you could write the solution, which is now we are denoting as yc, as c1 y1, which is these y's are also function of this t, but I'm not writing them explicitly, and c2 y2, right? So this is just your yc, that whenever you solve the homogeneous system you get the complementary solution, and this particular solution will be coming from this f of t. That is when you want to deal with this f of t. And it is very easy to check that this thing as a whole this thing satisfies equation 1. And to find a particular solution, one needs to choose some form. So a particular solution will have the following form in general. Let's write e to the power s, and again I will explain these terms. E to the power lambda t, you have a n, which is a function of t, that is an n degree polynomial. Then you will have cosine mu t, you have something called a bn, and then you will have sine mu t. So what is s? S means the root repeated n times, that is the equation of multiplicity. So it is the multiplicity factor. Again, let's say you have an auxiliary. Let me just show you what do I mean by this. Let's say you have an auxiliary equation as r square plus 2r plus 1 equals to 0. That means r plus 1 square equals to 0. So here you will have r plus minus I, right? So, oh sorry, not r plus minus I, my mistake. You will have r is equals to minus 1, but you have this is a second degree equation, and it should have two roots, but this time the root is getting repeated 2 times. So for here s will be 2. So this will be more clear that when we discuss another example. So this is our multiplicity factor, and the roots are linear combination of this lambda and mu's that you saw before. That is lambda and mu. Again, I'm going to write them down. They are coming from the roots, of the auxiliary equation. And an and bn are just polynomials, n degree polynomials. So we have everything on board, and let's try to use these things to solve a problem. Because if you don't see examples, then these things are pretty confusing. So the first example that we're going to see, let's call this example 1, is that you have an equation y double prime minus 4y prime plus 4y, this is equals to 12t minus 6 times e to the power 2t. So the first step is to solve the homogeneous part first. Solve the homogeneous part to get the complementary solution, that is yc of t. So how to do that? That's pretty easy. This is just y double prime, so it will be r square minus 4r, that is, I'm writing down the auxiliary equations directly, and you have 4 equals to 0. So this means r minus 2 whole square. Am I right? Yeah, r minus 2 whole square, right, is equals to 0. So you can write r1 equals to r2 equals to 2. So we have our roots, and we also can write down the solution immediately using the techniques we have seen before. That is, the complementary solution will be something like c1 plus c2t e to the power r, that is, this r1 and r2 are equal, right? So this is just 2t. Now second step is to find the particular solution. Find the yp. To find yp, first you note this multiplicity. Notice the multiplicity, and you can easily understand from here, that is this power, that it is 2. So first we write s is equals to 2. Alright, and if you see from here, that is this line over here, this function can take this kind of form, and our roots came as a form that you saw in the previous lectures. The roots came in the form as lambda plus mu I, right? And here you can see that this lambda part is real and mu part is my imaginary part. So in this example, lambda equals to 2, so let me just write that down, lambda equals to 2 and mu equals to 0, right? Okay, good. So if that's the case, then we are almost through, and now just what we have to do, we have to put these values, that is the values of lambda and mu and s, into this equation, that is this one over here, since we are searching for a particular solution. So you have to put the value of s, that is s equals to 2 over here, lambda equals to, sorry, s equals to 2 over here, lambda equals to 2 over here, and if you put mu equals to 0, this cosine mu, when mu equals to 0, this is just 1, and this guy goes away, that is, it goes to 0 when mu equals to 0, because sine 0 is just 0. But what about this an, right? What about this an? That how many degrees of polynomial that you should take? The idea is to look at the function over here. Let me just highlight it with another color. That is this one. This is a first degree polynomial. So a general first degree polynomial has a form of alpha 0 plus alpha 1 t, like this, right? So we are going to take this form, and now let's try to construct the solution. So the solution will have the form y of p, which is a function of time. We are putting s equals to 2, so there will be t squared, right? According to this theory over here, that is the yp, the general form. Then you will have lambda equals to 2, so it will be 2 to the power, sorry, e to the power 2t, and then you have to find this a of n, that is a general first order polynomial. So let's write this as alpha 0 plus alpha 1 t. But now what to do, because we have two unknown parameters, or two unknown undetermined coefficient, that is alpha 0 and alpha 1. So the last step is to find find alpha 0 and alpha 1. To do that, if you recall that our total solution yt, which was yc plus yp, they satisfied this equation, that is equation 1, right? And if you bring this guy over here, let's call this 2, into this equation, it would decouple into two parts. One will be a y double prime c, then b y prime of c, that is the complementary solutions, that is coming from the homogeneous part. Oh, there should be a y over here. Yeah, cyc. It's just a matter of differentiation and you can easily verify it. So I'm just writing it down directly, and then you'll have a yp double prime b yp prime cyp, and this will be equals to f of t, right? But this is coming from, that is this part is just the homogeneous part, because yc came from solving ay double prime plus by prime plus cy equals to 0. So yc is a solution of this guy, and this whole thing goes to 0. And as you can see, you have some equality over here, so we are going to use this equality. So let's write that. So we are going to differentiate this yp 2 times first, and if you recall that our equation had a equals to 1, b equals to -4, c equals to 4. So we are going to use these things. We are going to differentiate yp, and finally we are going to write this whole situation that is emerging over here, and then we'll try to find the coefficients. So bear with me. The yp double prime, first you have to evaluate that, then you have to just put all of this, that is you calculate this guy, you just have to differentiate with respect to time. So I'm not writing that directly because it will take a lot of time. And finally you will have over here yp is equals to f of t, right? This f of t was 12t minus 6 e to the power 2t. Now if you do all this, that is you differentiate 2 times, you differentiate 1 times, and then you just plug the value of y of p, which is just a differentiation of a single variable, then on the left hand side you should have 6 alpha 0, sorry, not alpha 0, it should be alpha 1, sorry, 6 alpha 1t plus 2 alpha 0 times e to the power 2t, and on the right hand side you have our f of t, which is just 12t minus 6 e to the power 2t, and from these both sides you can factor out this e to the power 2t, and then what you need to do, you need to write this whole thing again. And if you just compare, oh sorry, I missed a plus sign over here, yeah, and this is a t. So if you now just compare the coefficients, so now you have to compare the coefficient. Now compare the coefficients, that is t has a coefficient of 12 on the right hand side, and t has a coefficient of 6 alpha 1 on the left hand side. So you have to write 6 alpha 1 is equals to 12, and here you can see that constants are appearing, they should also be equal to each other, and you can think of it like coefficients of t to the power 0. You can always think of these constants like this as well. So on the right hand side the coefficient is 2 alpha 0, and then on the on the left hand side it is 2 alpha 0, and on the right hand side it's minus 6. So just write 2 alpha 0 is equals to minus 6, and if you solve them you have alpha 1 is equals to 2 and alpha 0 is equals to minus 3, and that's it, we are done. So finally you can write the particular solution, which is a function of time, as 2t minus, because if you recall that yp of t had a form of t square e to the power 2t then alpha 1t plus alpha 0, right? So I'm just writing this alpha part in the first place. So there will be 2t minus 3, then there will be t square e to the power 2t, and finally the full solution y of t will be just yc plus yp, and if up to this point you are done. So this is how you can easily solve some nice equations. That's the reason I'm saying nice, because most of the times you might see some functions on the right hand side that are pretty difficult to do with this method, and a word of caution is that this method will not always work, and that's why we have chosen this long example so that I can explain to you how this method works. But most of the time this method is like a wild goose chasing. If you do it systematically and you have some nice functions, you can do it with this method, but most of the time it might not work. It may not work as, yeah. So we're going to see another method that is called a variation of parameter in the next video, and that method will work when this method, that is the method of undetermined coefficient, is not working. So that's why I choose only one example, and this is a pretty long example, but I hope you got the point that how to work. So this will be it for today, and I'll see you guys on the next lecture. Thank you.